Every single year, the sheer volume of new clinical data, procedural updates, and specialized medical literature expands exponentially. This graph plots that sharply rising exponential curve of medical knowledge against a flat horizontal baseline representing standard medical training hours. Medical education hasn't scaled to match this data, creating a widening deficit in clinical readiness. Bridging this requires a mechanism for higher knowledge retention. By integrating artificial intelligence with gamification, educators build adaptive learning systems that maximize the efficiency of every available training hour. Gamification, in this context, refers to the strategic application of specific game mechanics, like scoring systems, detailed progression trees, and immediate feedback loops, integrating them directly into standard clinical curricula. If the medical field cannot solve this ratio of expanding knowledge to fixed time, the baseline standard of clinical proficiency faces a significant bottleneck. Engineering an adaptive curriculum offers a systemic path forward. In professional training, gamification serves as a psychological tool for driving specific behavioral outcomes and encouraging long-term knowledge retention. This architectural schematic outlines self-determination theory. For any system to generate genuine intrinsic motivation, it must satisfy three core psychological needs: competence, autonomy, and social inclusion. In a clinical training environment, competence is validated through tangible progression. As a student masters a diagnostic skill, the system issues an achievement badge, providing immediate, quantified verification of their capability. Autonomy is satisfied by offering branching, self-paced learning pathways, allowing trainees to direct their own focus. Social inclusion is driven by leaderboards that benchmark performance against peers. The primary flaw in traditional gamification is rigidity. A fixed system impacts diverse psychological profiles in different ways. For instance, a highly competitive leaderboard that motivates an extroverted resident can actively stress an introverted one. Optimizing the learning environment for a narrow subset of personalities inherently limits the efficacy of a medical curriculum intended for a diverse workforce. Integrating artificial intelligence addresses this limitation. Machine learning algorithms serve as an active personalization layer, adjusting the mechanics of the curriculum for each individual. As the trainee interacts with the platform, the system captures a continuous stream of granular data, error rates, reaction times, and learning pace, feeding it directly into the algorithmic engine. The model analyzes this input to deduce the user's personality profile, then alters the psychological levers in real time. The system might swap a public leaderboard for a private, mastery-based tracking system if it detects a profile that responds poorly to overt competition. This continuous data analysis also enables dynamic difficulty adjustment. The algorithm scales the complexity of an upcoming medical scenario based entirely on the user's performance in the immediately preceding tasks. By calibrating the challenge level at every step, the system prevents boredom from easy material and frustration from overwhelming tasks, anchoring the learner in their optimal zone for skill acquisition. AI effectively transforms a one-size-fits-all model into a precision learning environment, extracting maximum value from the trainee's available time. Applying this personalized architecture to high-stakes clinical scenarios proves its utility, particularly when addressing pervasive systemic errors like low-value medical practices. A low-value practice is any clinical procedure or test where the potential physical or financial risk to the patient outweighs the anticipated medical benefit. This dashboard for an AI-powered virtual patient simulation demonstrates how educators can target and correct these habits. These realistic, simulated environments allow medical students to execute complex clinical reasoning, order tests, and design treatment plans entirely free of real-world risk. If a trainee prescribes a low-value procedure, the underlying AI logic instantly reroutes the diagnostic decision tree. The simulation adapts, forcing the student to navigate the negative cascading effects of their specific choice in real time. Engineering a controlled, adaptive environment where students can fail at complex clinical reasoning is an efficient method to identify and correct errors before they translate into real-world patient harm. Clinical practice is a cooperative effort, meaning the scope of adaptive education must extend to community-driven, team-based learning. Natural language processing, or NLP, facilitates this network of knowledge sharing by allowing the system to interpret and organize unstructured collaborative input. For instance, cohorts of students can interact with NLP models to collaboratively build specialized clinical dictionaries for new procedures, or translate complex do-not-do lists into actionable team protocols. Because the NLP model acts as a central machine learning repository, it captures and validates these student-led contributions. This allows the project to transition into a self-maintaining institutional resource that evolves as medical terminology and best practices change. Modern healthcare organizations rely on highly cooperative workflows. Leveraging AI to construct these collaborative learning skills is as critical to a physician's success as their individual diagnostic accuracy. Deploying these advanced systems presents immediate systemic bottlenecks. Building sophisticated algorithmic learning platforms requires high upfront financial investment in complex data acquisition pipelines. Furthermore, platforms analyzing user behavior must adhere to the strictest e-health cybersecurity standards to ensure the privacy of trainee profiles and any integrated patient data. Beyond logistics, there is an ethical tension. Poorly designed gamification carries the risk of degrading collaborative medical culture into an environment of high-stress rivalry. Without careful calibration, these platforms can cross a threshold into what researchers term exploitationware. Exploitationware occurs when the systemic drive to accumulate virtual rewards overshadows the value of actual patient care, generating undue psychological pressure and fracturing institutional teamwork. Unless medical institutions enforce a rigorous, standardized ethical framework, the deployment of gamified mechanics can actively erode the operational safety of the hospital environment. To justify the integration of AI curricula, the industry must move past measuring short-term engagement and prioritize the evaluation of long-term clinical efficacy. This requires launching randomized controlled trials to compare the clinical performance of cohorts trained on AI gamified platforms against those progressing through traditional models. It also necessitates longitudinal cohort studies designed to track the retention of specialized diagnostic skills over years of postgraduate medical practice. The ultimate evaluation metric is transferability. Educators must determine if the clinical reasoning honed inside a virtual simulation directly improves decision-making at a physical bedside. These algorithms are powerful tools for accelerating competency, but they remain in service of the practitioner, acting as a supplement to clinical experience. AI-powered gamification focuses on engineering a training environment that provides the rigorous, individualized feedback necessary to equip the next generation of medical professionals.